Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, thank you for coming this morning. It's my pleasure to have Jonathan Protsenko visiting us for the next couple of days while interviewing at the RISE group. Jonathan's going to tell us about some work he's been doing on Mezzo, an ML-like programming language with a type system that's inspired by separation logic. And what's also cool is that Jonathan's a bit of a doppelganger. He's got a second life as a web developer doing open source development for on various Mozilla projects, and if I understand correctly, maintains one of the extensions for Thunderbird that's got more than 100,000 users or so. So that's pretty awesome. So looking forward to hearing about both these things, maybe more about Mezzo than about the other, but both too. So welcome.
All right. Thanks, Nikhil, for the introduction. As Nikhil said, that talk is going to be about my research, and it's mostly going to revolve around Mezzo, the language that I designed during my PhD. So there's going to be three main axes to this presentation. First of all, I'm going to tell you about the design of it, and then how we implemented it, and then I'm going to tell you about the user interaction, and that's where the visualizations and all the fancy demos are going to come in. So quickly, a word about myself. I flew in from INRIA back in France, and I'm in the Gallium team, which you certainly know for some of the famous projects such as OCaml or ComCert. My advisor is François Potier, and as Nikhil said, I happen to be a Mozilla contributor. My PhD work was really Mezzo, the language. It's been all about designing it, and what we've been trying to do is provide language that's introduced in the tradition of ML, but that goes further, right, using the type system. It goes further, it provides more guarantees about three buzzwords, if I may say so, which are state, ownership, and aliasing. So hopefully it'll be more clear by the end of the talk what I mean by this, but really the key points that I'm going to cover, among other things, are first of all, I'm going to tell you how we designed the core of Mezzo, how we combined various ingredients from the literature to create what we believe is an interesting core calculus. Then will come the problem of complex aliasing. You have an arbitrary graph of objects, pointers in every possible direction. What is our strategy for dealing with that? I'm going to tell you a little bit about the implementation, since that's one major fragment of my PhD. Why was it hard implementing Mezzo, and how is it done? And then I'm going to tell you a word about the visualizations. So really that talk is going to be sprinkled with demos and visualizations. And hopefully that'll make it more interactive. And really, if there's anything that's unclear, I really do wish to be interrupted to make sure that no one is lost, and I think it's going to be better for everyone if you ask questions in the middle of it. So I like to start this talk with a small example of what I think is a bad programming language. That's the control equations for Apollo 11, the lunar landing, and the comments are really interesting. It reads temporary, I hope, 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 and they landed people on the moon with that. So there's a... It's actually on Google Code. There's been a release of all the old documents, so you can actually read the original control programs.
No harm in starting bugs.
Yeah. So back then, there were some pretty bad programming languages, but...
There's another way of looking at it. It means that verification is not needed, because we managed to land something on the moon without
right.
such a terrible programming language.
I wouldn't want to fly to the moon with that program. So people quickly realized that we needed better programming languages. A guy called Knuth said, I think we're on the verge of discovering at last what programming languages should really be like. By 1984, consensus for a really good programming language. Right. So it turns out that's not quite the story. That's an example that I kind of like. There's a variable which is equal to itself and also equal to not itself. So what I won't tell you is not, I don't want to bash any language. What I want to say is the quest for better programming languages goes on. It is still an open problem. And why do we want better programming languages? We want better programming languages to better reason about your programs. If you're landing a guy on the moon, you want to have maximal confidence that the program does what it intends to do. And one way to attain that goal is to have better programming languages that, from the start, rule out more bugs. And that's what I've been trying to do. And the way I've been trying to do it is through type system. Type system is a strong component for my team, and really we wanted to go the next step. There's the famous Lunar motto, well, type programs do not go wrong. We really want to take it to the next level. And the way we did it through a type system is that, in our opinion, there's a lot of advantages to doing it through a type system. It's part of the workflow. It's every time you program, you got to think about your types. If you want to port a program to a better type system, you can do it incrementally. You don't have to rewrite the code. You can just improve on the types. It's one layer. You don't have like a verification layer on the one hand and your program on the other hand. And also, what we are really trying to achieve is a compromise. We don't want full specification. We just want a better type system that gives you more guarantees. And really the end hope is that programs that are written in Mezzo, because they've been written using that fancy type system, are more structured, meaning they're more likely to be proved if someone wishes to do so. So Mezzo feels like ML. Really, the syntax looks like ML. It's very familiar, but the type system is closer, I would say, to separation logic. It allows you to talk about state. I don't know, is my socket initialized or ready or closed? Ownership. I have that piece of mutable data, which thread owns it. And aliasing. I have many, many pointers. How do I manage that? And again, I really wish to stress that Mezzo is not the ultimate answer. It is not going to provide you with a complete specification of your program, just stronger guarantees while hopefully remaining somehow manageable. The reason we're doing that, and I really should clarify how we stand with regards to it, is concurrency. The end goal is to have a better type system for helping you write concurrent programs. The initial effort was aimed at sequential programs because there's a lot of things that you have to sort out before you move on to talking about concurrency. Working on sequential programs has allowed us to incorporate new idioms to make the type sister understand more stuff. It allows us to talk about effects, and then it allowed us to gain that guarantee. One of the main theorems that we have is that programs in Mezzo are data erase-free. So what we have now is a lot of modules that are formalized in Mezzo for locks, concurrency, threads, channels. However, the main caveat is that we do not have a concurrent runtime. I just want to be clear about that. We're using OCaml's model, which is not parallel. So the future would maybe to move to a better runtime. We formalized and we set the mechanisms for talking about it, but we don't have parallel execution in Mezzo as of now. Before jumping in right to the examples, I just want to tell you about a few sources of inspiration that we had so that hopefully...
Can I just ask a question about the previous slide?
Yeah, sure.
So you're saying that you support threads, but they can run only on a single core.
Yes.
So you'll make sure that the operating system doesn't context switch?
No, what I mean is that we have signatures for the spawn function in our type system. We can type check the spawn function with a very fine-grained type that tells you what the thread modifies in the heap, etc. But ultimately, there is only one thread that's running in the runtime system of OCaml. We do not have multiple threads. It's just sequential. Programs are compiled sequentially. Actually, I think the thread module does not even compile. You cannot use it. I mean, there's a type checker interface for it. It's formalized. It's modeled. But we do not have any support for running threads right now.
So once you verify the program, why would you even run it? What? No, I don't understand.
No, I guess the question was, you said not truly parallel, but you could be supporting switching between threads on a single process.
Yes, correct. We do not even do that. I mean,
You don't even do that.
our effort was really in the design of a language, not in the implementation of a runtime system.
So if I have a blocking primitive, like I don't,
Yeah, would that deadlock the program?
that would deadlock the program if I ran.
It would just be like, what kind of blocking primitive?
Like supposing I acquire a lock.
Block.
I don't think locks are implemented right now. I mean, they have signatures. You can write a program that has
Okay,
locks.
so there's no.
I mean,
okay, right, it's not.
It's very primitive. I mean, we have a compiler just to say that we can run basic programs that do print.
I get the drift now.
Okay.
Yes.
It really is about the design of a type system, not. Okay.
So it's nothing deep to extend. You could, in principle, with some engineering, have a runtime that does this stuff.
Absolutely. I mean, it's just some missing manpower. We just need to, fill in the gaps in the compilation tool chain.
Dexter will be fine with this.
Okay.
So you use the OCaml runtime in Mezzo,
Yeah, the way we do it is that the compiler translates Mezzo code to a camel code.
but Mezzo code has nothing to do with OCaml otherwise.
No, I mean, you can interact between the two. You can call Mezzo code from a camel, but again, our focus has been on the design of the language and the proof of soundness. Right now, the compiler outputs an OCaml file with several calls to obj.magic because the type system of Mezzo is more powerful. And then you just compile it and run it. We have some very basic sample programs. Any other questions? Okay. So let me just give you a few sources of inspiration to make sure that we can locate Mezzo in the design space. Mezzo is influenced by a lot of existing work. Of course, there's the linear lambda calculus, which has that idea that some variables may only be used once, and that way you get predictable deallocation, and that's an efficient way to model system resources. So we do have that notion also in Mezzo that some variables can be uniquely used or have a unique order. Another source of inspiration is alias types. Maybe, in my opinion, the main idea in alias types is that you want to keep track of aliasing relationships in the type system. You want to remember that this field of this object and this other field point to the same thing, and that's encoded in type system. And we have a similar mechanism in Mezzo. Separation logic is probably our main source of inspiration. The fact that we have a star that can possibly separate distinct fragments of the heap. The fact that you can have local reasoning on a function and you know that whenever it touches its own fragment of the heap, it will not interfere with whatever lies everywhere else. The frame rule, these are all things that are, in a way, that appear in some way in Mezzo. Another source of inspiration has been object-oriented languages. There's that Plaid family of languages where people have a language that feels like Java, that has a type system, and on top of that, they have a reasoning about permissions, and they want to model object protocols like iterator, has next, ready, or closed. So they have state diagrams, and they want to model that, and we also have something similar in Mezzo. And finally, a paper that I quite like is the one about ownership types. There's a lot of great ideas in the paper, the fact that there's an ownership hierarchy, that objects may own others, and also an essential idea that we also have is that you may have a pointer to an object, but you may not have ownership of it. And that's something that I will elaborate in this talk. So that's pretty much all for the intro about the language. I'm going to directly jump into some demos. So there's going to be several self-contained examples. I'm going to switch back and forth between Mezzo and this presentation, and I'm going to do some quick recaps. So if anything, the syntax or what I say is unclear, please do interrupt me. I'm going to start with a usage protocol, which I call the write once references. Say you're parsing your command line options. You have some uninitialized memory. You're going to initialize it once, and never after again are you going to modify it. And say you want to encode that in the type system. So you start with a new write once reference, which is in the state writable. Then you seal it. So seal has two effects. It writes something into the reference, and then it makes it immutable. So you can no longer write into it. And then once in the frozen state, you can call get repeatedly, which keeps you in the frozen state. So here's some code that does that in Mezzo. It constructs a value which is unnamed, and which is a pair of integers by allocating a new write once reference, sealing it, and calling get twice. So how do we reason type system-wise about that example? Type checking in Mezzo is flow sensitive. So we start here, and we say that we have the empty permission. A permission, Mezzo, is something that has this form with an @ sign. For instance, if you call new, you get a new permission for R, which tells you that R has type writable. So a permission conveys two types of information. It tells you about the shape of the object in memory. R is a writable memory cell, which has a contents field, for instance. And it also tells you something very important. It tells you that because R is writable, you have ownership of it. You own the fraction of memory that is pointed to by R. How you own it is going to depend on the nature of the type. I will get back to that later. But if you have that permission, you have a certain ownership for R. What happens that you call seal, we'll see in a minute the signature of the seal function, but it expresses the fact that it needs to have this as a writable, and it transforms it into something that's frozen. The signature of seal expresses that. So actually the permission disappears, and another one appears. So really permissions, they come and go, and they may change through execution. Permissions, they're completely in the type system. They do not exist at runtime. It is our type system. We don't have a separate judgment with a gamma. This is what we use for our type system. Is that clear so far? OK. I think I have a demo. OK, so can everyone see properly? OK, let me click on write once references. So and I'm going to clear this. So that's Mezzo in a web browser. I've compiled Mezzo to JavaScript, and it type checks in your browser. I'm not connected to the internet, so it's not sending off anything offline for some other server to type check. So it may be a little bit slow because it's JavaScript, but it's still fairly acceptable. So that's the implementation of write once references. Basically, we're, yeah.
Can you use the pointer on your PC rather than the Wii pointer?
Sure.
Yeah.
So that is the definition of a data type. That's the writable data type. It only has one field, contents, which has type units. So it's just a placeholder value. It's mutable, because there's the keyword. And then the frozen type also have a contents field, except the contents field has type A. And because there's no mutable keyword, it is immutable. The new function, well, it just returns to you a new writable with a placeholder value in it. And the interesting bit here is the seal function. The seal function tells you that it takes ownership from its caller of a thing called R, which is a writable. It also takes ownership of X. So that's the special consumes keyword here. It tells you that you're stealing from your caller the two permissions, and in exchange, you're returning a new one to your caller. You're returning to your caller a permission for that very variable R, and you're returning to it the fact that it's now frozen. The function operationally does two things. It writes X into the contents field, and it writes into the tag of R the frozen tag, which basically amounts to telling the type system that the thing is now frozen. And finally, the get function, it just takes a reference R, and it returns a pointer to the contents field.
Sorry, what's the pipe on line 13?
Yes. So the pipe is to separate, it's the conjunction of a type and a permission. So if you write T pipe P, it's a value that has type T along with a permission P. So if you have the unit value along with permission P, that's written like this, and we somehow abbreviate it as this. So it's the unit value along with conceptually a permission. Any other question about the syntax? Yes?
So consumes means you take the ownership. So if you do get, like no, that seems like nobody else can get anymore.
That is an excellent question, which is going to be addressed in ref get fixed too. I'm going to get to that in a minute. We did not coordinate with Dan so that he would ask me the question. Yes.
Two questions. So in the previous slide, you had writable and frozen, and here you have writable and frozen, and where they're declared as types, no, they're not built into the language.
Yes.
So I guess that they were not built in the previous slide, right? They referred to these types.
Yes, absolutely.
But what's built in is the consumes.
Yes, consumes is a built-in
And
concept.
the pipe.
Yes.
So now in the seal function you have R dot contents, and when you pass in R, it's a writable that has a unit in the
Yes.
contents field.
So let me show you.
Override it with an alpha.
Yeah. So let me show you.
And so this wouldn't type check in simple types, right?
Absolutely, there is actually a state change that takes place. The variable goes through different types. So initially, we have R at writable, but the type system is aware of the fact that writable only has one branch, so it expands that as what we call a concrete type. It's basically a type that tells you about the structure of R in memory, So that's a more precise type that tells you that there's a writable tag, and then there's a contents field which has type unit. And the system knows how to deal with that in the sense that if you assign something into the contents field, it's going to keep track of that change by saying that the contents field has type A. Okay, so we are in an intermediary state. We have somehow broken the invariance. That type cannot be seen as a writable and cannot be seen as a frozen either. It's something in between. The type system keeps track of that. It allows you to temporarily break invariance, and then on the next step, you change the tag. So you just modify the writable portion of it, and you write frozen instead. And then the type checking says, the post condition of that function says that I have to have R as a frozen thing. Is it actually a frozen? Yes, because this is a subtype of R at frozen A. So subtyping takes place, and then you get what the post condition of the function requires.
And the data declaration declares records and that have tags. So
Yes.
the tag keyword accesses the tag of the record.
Tag of is a keyword, yes. And when we say mutable here, it means that everything, the whole memory block, is mutable.
Both the
include-
tag and
Yes, absolutely.
so then frozen is not mutable.
No. So if I were to do another assignment here, like tag of R gets mutable, that would be an error because the thing has been frozen. It no longer is mutable.
So the type system can synthesize these intermediary types that aren't expressed anywhere else in the program, like a writable with a content.
You can write that type. You can actually write it. You can write that type. I could have said here, instead of writable, I could have said R writable contents unit. That's pretty much the same thing.
Yes, but when you assign something to the contents, and now you have a writable with contents that's not unit, that's not described anywhere else in the program. It just synthesizes these on the
Yeah,
fly.
it is aware of that. It is aware of that, and you could actually write it here. Like, say I wanted to give it a somehow different signature. Let's say I'm going to do something stupid. I want to only initialize writables that originally contain integers. You can write that intermediary type. Okay. So, quick recap. Permissions, they're available at each program point. They change as you step through the program. So type checking is flow sensitive. The functions have in their signatures the effects that they perform, and the permissions, they are our type system. And here we've been talking about state. So for us, the state of an object, it's simply the type that it has. It may move from type A to type B through a function call. Okay, I'm going to show you another example, which is that of a race that is rejected by the type system of Mezzo. Whoops, not this, this. So I have a variable R, which is a regular reference. So I'm just calling the built-in new ref. New ref has an implementation that just defines ref contents. So it's just regular references. And there's an incur function that mentions in its signature that it modifies R. Because there's no consumes keyword, it takes ownership of R and it also returns it. That's the syntactic convention. If you do not have the consumes keyword, you're just modifying your permissions. So incur does not take a pointer to R, it just modifies it. It closes over the pointer. And it basically assigns R plus 1 into R. So let's say that I want to start 2 threads that only do incur. What do I have in terms of permission at that program point? I have R, which is a reference, and I also have a permission for incur, which is a big function type. I want to call it spawn, because incur requires the permission for R. After I've called spawn for the first time, I no longer have the permission for R. So if I try to call spawn for incur another time, that is going to fail because the required permission is no longer there. So let's try to type check this. I hit go. It tells me that at the highlighted location, I could not obtain the permission for R as a reference to an integer. It tells me that there's only another lesser permission available for it, which I will mention in this example. Okay. So how does that work? The system has a built-in notion of what is shareable and what is not shareable. For things that are mutable, it knows that they must have a unique owner. Because, say, if you modify a thing and you put it into another state, if someone else still owns a copy of the permission that points to the older state, you're going to have an inconsistency. So anything that's mutable must have a unique owner, and the system is aware of that.
Is it possible to see the signature of spawn?
Yes, I suppose. Let's look up in the standard library. Not there. Let's look up in the core library. Yeah, here's the signature of spawn. It basically takes a function f that requires a certain permission p. The outer spawn function also takes itself the permission p, and it runs f by conceptually passing it the permission p. You're basically expressing the transfer of ownership. Spawn takes from its caller p, transfers it to f, and starts f on a new thread.
And Inker actually, it doesn't quite consume a permission, right? It takes it and gives it back in some sense.
Correct.
And you have some kind of subtyping of some sort?
Yes, I'm pretty sure that there's subtyping going on where we're dropping the permission.
Okay.
The syntactic sugar for without consumes translates to a permission that's consumed in the argument and returned, and you can just drop it in the code domain of the function. Okay. Yes. So there's a built-in notion of what is duplicable and what is not. Data may be frozen from mutable to immutable, but of course not the other way around. For that would be unsound. Let me just now move on to another example, which is an aliasing violation. By the way, there's a way to fix the race, which is to use a lock. And that I'm just going to run over that example quickly, but this is a higher order function that transforms a function f that has some internal state s into a function that no longer exposes its internal state by allocating a new lock. So what the function hide does is that it allocates a new lock for the function's internal state, and it creates a new function that has no internal state. First thing, it acquires the lock, calls the original function, and then releases the lock. So it's hiding the internal state of a function in a higher order way. And if you call hide on Inker, you're basically getting a function from unit to unit, and that function, you can spawn it twice. If I clear this, I think I can type check that example. Okay, it's a little bit long. Yes, type check successfully in about 3 seconds. Okay.
For me, that's strange because I don't think you really hide the internal state because it's observable. But what you really mean is you're saying you hide kind of the permissions of that.
Yes.
Such that you can use it in a multi-threaded way.
Yes.
But you still guarantee the data race freedom.
Yes, absolutely.
Right.
That's what the fact that this program type checks means. Thanks for rephrasing it in a better way than I did. So that example should make you happy. That is the usual get function for references. If I try to type check that example, it's going to tell me that I have an aliasing violation. Why? Because I'm pretending that I'm maintaining the argument r as a valid reference, but I'm also returning a pointer into the reference. So now I'm aliasing the contents field of the reference. I have one way to access it through r, and also through the return value that's returned by the function. So that's an aliasing violation. How can I fix that? The first natural way to fix it is to require that the reference contain duplicable elements, which I can then freely alias, and then this example becomes legal. But I can do something smarter. What I can do is use a special quantification. What I'm going to say is I'm going to return a pointer to the element x, which happens to be whatever is in the contents field of the reference. So what's that bizarre thing equals x? That's a type which we call a Singleton type. The Singleton type equals x is the type of elements that are equal to x. So that's the way, the only way we get dependent types in Mezzo. And what that tells you is that you just return a pointer to the element called x without any ownership information. So you're not attempting to duplicate ownership. you're just returning a pointer into it. The square brackets stand for universal quantification over x. So I'm going to run that example in a term. Yeah.
Term is another type?
It's a kind. It's the kind of variable. So that is a type variable at kind term. So program variables, if you do let x, you can use x in expressions, and it types with kind term.
Could you have written get square brackets a and x colon a?
That would have been embarrassing because that would you be. No, you cannot do that. No, that wouldn't work because a would have to be a kind here. And we do not quantify on kinds. So you can write for all a, but then a is a type.
Right, so you write for all a, and
Yeah.
then you also write for all x of type a.
Like this.
No,
Just in the...
it's just a second square bracket after the a, x colon a.
I think you said you don't support quantification over kinds.
Yeah, we don't support
I see.
that. So
I was thinking that this is just quantification over types, but
no, x is already a type variable
Okay.
of kind term. So
Okay.
that really means a of kind type,
I see.
and this is x of kind term.
X is already a type variable.
It is already a
so
type
you're
variable.
Doing it in Singleton type
Yes.
style. Okay.
Yes,
okay,
it is a dependent type.
Okay.
I'm just going to run that example in a terminal. Oh, I can barely. What appears in the terminal is not important. What is important is this. What I want to tell you is that the type checker, because of these Singleton types, keeps track of aliasing information. So let's move back to the example for a minute. What does the example do? It allocates x, which is a tuple. It allocates a new reference whose contents field is x, and it calls get r and stores the result in y. So I'm just going to put the two side by side. The type system knows that x and y are the same things. It knows that the contents field of r points to x, which also happens to be y, and it also knows that the tuple here has two components that are integers. So internally, the type checker has a graph of objects, and that is done through the mechanism of Singleton types. Why do we use Singleton types? Yes.
Okay, so the problem, suppose that x has a reference to 2 instead of just 2 has a pointer to 2.
I'm sorry?
Suppose that, so here you declared x as a, or defined x as a tuple,
Yeah.
1, 2.
Yeah.
If you declared x, or defined x as a tuple of ref1, ref2,
Yeah.
So then the state of x would be mutable.
Yes.
Your get function would still work because x and y are equal in your type system.
Yes.
But so does your type system then let you write programs without deep copying your values, or would you have to deep copy? When you started the examples, I was expecting a function, a get function that would perform a deep copy,
Okay.
but that seems not to be going on.
No, what happens really is that when you create an alias, like let x equals y, instead of deciding whether x or y gets the information, whether we have x at interesting stuff or y at interesting stuff, we just remember in the type system that x and y are the same thing. And that's where the Singleton types kick in. We have a special permission, x at equals y. And we just add that. We do not try to do a deep copy to make sure that both x and y are references. We do not try to assign ownership to the other one. We do not do borrowing, like x borrows the reference from y or something else. We just put that equation on the side, and the whole type checker is able to deal with the equations. It can perform rewriting and use one or another indifferently. And using Singleton types, we keep track of the aliasing relationship between program variables, tuple fields, and record fields.
Does this work with control flows? If you have
That is an excellent question. The short answer is we thought it would be a problem, and it basically never happen in practice. Whenever control flow diverges, I'm going to get to that later, we do a graph traversal in parallel, and we reconstruct maximal aliasing information, and we don't have problems in practice. I mean, we're able to reconstruct the aliasing information. So really a conjunction of permissions. It is a graphical description of the heap, and that's the way we think about it. I'm going to switch to a complete example. I am going to do the example of list concatenation. Let me just switch to my browser again. That is the definition of lists. It's either nil or cons. These are immutable lists. We have some helpers for constructing cons and nil, and we're doing append. So append, it's just like in ML. You match an excess. If it's nil, it's ys. Otherwise, you just create a new cell until ultimately you make it point to ys. The interesting bit, and the reason why I'm showing that example, is that there's a consumes keyword, because you have to take ownership from your caller of the tool lists. Otherwise, you would be creating aliases. Like if your caller can still point to the original list and the concatenation, the elements that are in xs and ys will be aliased. So the only way we can write that function is to ask it to require ownership and to steal ownership from the caller. That seems very restrictive, and indeed, well, when it's a list of references, because references are uniquely owned, the caller loses the ownership of the lists, right? If you try to assert that L1 is a list of references at this program point, that is not going to work. Let's try it. It tells you that it could not obtain the permission that L1 is a list of references to unit. So really the type system rules out this dangerous behavior. The good news, however, is that if your lists happen to be lists of integers, lists are immutable, integers are immutable. So L1 points to an immutable fragment of the heap, and the type checker knows that. It knows that this permission is duplicable, so it's safe to save a copy, use the copy for calling append, and then keeping a copy for yourself. So these assertions are actually going to work. And we call it call site polymorphism. Yes, type checked successfully. And the big example that I'm going to show you is that I'm going to write a tail recursive version of append. So we can already write a tail recursive append in ML by doing two passes. First rev append and then rev. But we can write it in one pass in Mezzo, and that is something that you cannot do in OCaml without resorting to unsafe implementation techniques. So how do you do tail recursive concatenation of lists in one pass? You use three types of cells. The yellow ones are cons cells. They are immutable, but they do not point to the start of a well-formed list. The blue cells, they're mutable. They have an uninitialized tail field. And the green cells, they point to well-formed lists. There's a loop, which we model as a recursive function. And the loop works as follows. You have created copies of xs, which are the yellow cells. And then you're basically trying to stitch dst onto ys by copying cells from xs. So this is a mutable cell. What you do is that you allocate a new blue cell, which is the copy of xs that you have to do. You perform pointer rewiring, because that is a mutable cell, and then you freeze the blue cell. So that's going to be one step, and you move forward as you go. You allocate cells on the fly. You rewire each cell to the next one until you reach ys, and in that case, you're done. You've created copies of xs, and then you've rewired the end of xs onto ys. So you have a well-formed list. The problem is the type checker does not know. There's more reasoning needed to prove that this is a well-formed list. You have to say ys is a well-formed list, dst is an immutable cons cell that has a tail field that points to a well-formed list. Therefore, it must be the case that dst is also a well-formed list. Nothing happens at runtime. This is pure reasoning.
What is well-formed list?
Something that has type list A. That is not a well-formed list because it ends up with a dangling tail field. So that is not a well-formed list.
So where is that type list defined?
I can show it to you. Yeah, this is list.
Okay.
And the definition of cell is basically same thing. There's a head and tail field. except the tail field is a placeholder and it's mutable. I think you had a...
Okay, very just interrupt too much.
Okay, and so yeah, after that, you're done doing operations at runtime, but you still need reasoning to unroll your recursion and to finally convince you that once the function is done, DST is the start of a well-formed list. I'm not going to show you step by step the entire example. What I want to show you is the tight loop here. It's the append aux function that I've been mentioning in the slides. Yes. What happens is that there's an additional reasoning that takes place at the type checker level after the recursive call. So basically, we're in a state where DST is our old blue cell, the one that has been made immutable, so it has a const type. DST prime is our new blue cell, tail is our new XS, and YS is the thing that we have to rewire ourselves on. The recursive call consumes the last 3 permissions and returns to you per its post condition the fact that DST prime is now a well-formed list. And we know that cons, that DST is a cons cell whose tail field points to DST prime. So it's basically the drawing that I made here. Previously, we were in that situation, and we are in that situation, and we need to perform the bit of recursive reasoning that tells us that DST is...
So I'm confused by one thing. So then, if you go back to the type definitions.
Yes?
So you're saying that the concept, but if you go up to the concept,
Yeah.
you're saying at some point you're allowing the tail to be something other than
Yes, absolutely.
widths. You're breaking in the implementation the listing variant.
Absolutely, that's the question that we had before, in the sense that we can represent concrete types that are not subtypes of a nominal type. We can represent a...
That's what you can't do in a camp.
Yes, absolutely. And for that, you need to have the reasoning that these things have a unique owner, because you're mutating them into something that's completely illegal.
Internally within this function, I can have some other types and I can wire things up
Yes.
to allow me to do this mutation.
Yes.
As long as in the end, I can prove everything is back at,
Yes.
At the level of these.
Precisely.
I
And
guess you don't even have to prove that at the end you're back at a list. You could return something in the middle with something in a funny shape.
you can
if like.
write these types if you want.
So suppose the data type cell has 2 cases, like cell and cell nil.
Yeah.
And now you change the tag
Yeah.
of dest to cons.
Yeah.
Your type checker would have to check that you're not taking a cell nil to cons, because you would lose. I mean, the record fields head and tail would not be defined in cell nil.
Yes, absolutely. Here, so the way it's stat checked is that here we have DST at cons. Cell. Head type A, tail equals DST prime. And there it checks that the size matches, that there's exactly 2 fields, and that it's legal to mutate the tag. The field names may be different, but the size of the block has to match per the runtime constraints. That is something that unfortunately we're exposing because we have runtime limitations. We can not expand in place GC blocks.
So the assertions after append outs, you say that DST is cons with DST prime, but then DST, but then you say that DST prime is least, but it isn't, right?
Where? Here, DST prime becomes a list.
Oh, after the call.
Yeah, after the call. Okay. That is the past condition of append aux. You pass it a thing, and it turns the thing into a well-formed list. Mm-hmm. So you pass it DST prime, and it turns DST prime into a well-formed list. And then there's the last step of reasoning, saying that if DST is a cons cell, its tail points to a well-formed list, then also it must be the case that it is a well-formed list. And the type checker knows that and performs that automatically. These are just comments. These are no hints to the type checker. That's just comments to explain what's happening. Okay. So I think I've explained that enough. The pattern works because we have tail recursive reasoning, that is reasoning that takes place after the recursive call, and we have state change and freezing of mutable data. So I'm done explaining to you the base layer of Mezzo. These are all the mechanisms that we're using, Singleton types, the notion of is duplicable versus is not duplicable, and these intermediary states that are not a nominal type. So with that, we can express several usage patterns, borrowing an element from a list, in-place link reversal. Basically, anything that has a tree-shaped aliasing pattern works. And that is restrictive. Somehow, you may want to have arbitrary aliasing. And that's my next part. I'm going to tell you how we deal with the problem. So you have an object that owns other objects that owns other objects. And you don't have back pointers. So typically, the example that we cannot express is that of a graph. In the graph, you have pointers in every possible direction between nodes. And you cannot make it in a way that a node owns its neighbors, because there's different pointers, and that would be an ownership violation.
But there's an intermediate, which is DAGs. So you can have some sort of DAG, right? You can have a tree with an internal point.
Ownership has to be
But
unique.
that would be an ownership violation, because you would have two objects pointing to the same thing. So who owns them? We can represent local
Yes.
aliasing using the Singleton types, but as soon as it's arbitrarily sized, we can no longer express it with the mechanisms that I have shown you so far. And actually, let's do it. Let's try
So
to.
tree means just everything is owned by at most once.
Yes,
One.
precisely. Yeah.
Exactly.
Yeah.
So, but in a graph, not everything is owned exactly once. So do you mean that the graph is a tree with back edges? Or?
In a graph, you cannot express a graph with what I've shown you. I mean, the graph definition would not type check. That's my example,
You
actually.
can't even do a DAG.
You can even do that, yes.
By the way, supposing, I mean, is it not possible to just do ordinary programming if I don't want to use all the fancy type system? And I just want to write a graph algorithm, can I do it?
You have to use the escape mechanism. We have a escape hatch, if you will, that allows you to break out of the restrictions of the base layer. But you have to be careful.
You said that it compiled down to OCaml. So does that mean that you could write your graph algorithm in OCaml and do that and link it against a program written in Mezzo?
You could. I don't think I've gone beyond the stage of a simple example program, but yes, in theory, you can link them because.
But you're not a superset of OCaml, right? You're not like allowing.
Oh no, we are different in the sense that we are ruling out programs that are valid OCaml because we think they're too dangerous.
Right.
They're doing insane stuff with their aliasing.
Right.
And conversely, we're also allowing behaviors such as the recursive function that are more fine-grained.
So it's not a subset or a superset.
No. So if you want to interact with OCaml, you could technically, because Mezzo programs can link with OCaml programs, but you'd have to be very, very careful. So what I'm trying to do here is I'm trying to create the graph with one node that points to itself. So basically a node just has a list of neighbors, and I'm going to do it in a naive way, and that's going to fail. I'm going to say that neighbors is a list of nodes, and that nodes hold a value. And I want to create the node that points to itself. So I'm initializing x as a node. Again, I'm putting a placeholder value in the neighbor field because I don't know what to write in there yet. And then I'm going to create a list of nodes so as to write it in the neighbors field. And that is going to fail. The reason it fails is that you already consume the permission for x as a node in order to create the list, and then the permission is gone. So you no longer have any useful permission for x. You no longer know that x has a neighbors field because that permission has been used already. So you can't do it. It tells you that the only permission you have for x is that permission called x at dynamic. So it has appeared already in the examples. So let me show you what x at dynamic means. That's going to be our escape hatch. So I'm changing the definition slightly. I'm adding a scene field because I'm going to do a higher order graph traversal. So I need to remember which nodes I visited. But more importantly, I'm changing the definition of neighbors to be list of dynamic. And now I'm defining a graph to be just a record with a list of roots, along with a special directive called adopts node A. And we're going to see on the concrete example how that works out. So here I'm creating G, which is a graph that holds integers with one node that points to itself. So again, I'm creating the node. But what I'm going to do here is that instead of creating a list of nodes, I'm going to create a list of dynamic. Because I've used the permission x at dynamic, I'm still left with the permission x at node. So I still have the information that x is a node. So I still can write into it. The good thing is, x at dynamic, it's duplicable. So even after that line, I still have it. I can ask for some information about x. Oops, sorry. I can call info x. And it's going to tell me that at this program point, I still possess the permission x at node. I think it didn't. Yeah, I still possess the permission x at node. And I also still possess the permission x at dynamic. So you also notice that it knows that the neighbors field of x is a cons cell.
That's cool. So you extend the programming language with features that let you kind of call back into the type checker so that it
Yes.
gives you some information.
Yes, that's a special hook that allows me to poke into the type checker, and the type checker knows about that special function, and it dumps some information about a variable. That's very helpful for debugging. So the important bit is that I still have that permission x at dynamic, so I can use it once more to create the list of roots for the graph. And now I'm using a special instruction called give x to g. So what does that mean? It means that I'm relinquishing, I'm giving up my ownership of x in order to transfer it to g. So I'm giving up on x. I no longer own x, but g owns x. How is that type check? I see that g is a graph. That graphs, they adopt nodes. X is a node, so it's legal for me to give x to g. And after that,
Now your ownership is about data owning data.
yes.
Usually ownership is about code access, right? Now you're
Absolutely. Objects are allowed to own other objects.
Other objects, okay.
Yes. And now it tells me that at this program point, the permissions that I have left for x are just x at dynamic. And that's good because I no longer have ownership of x. I have ownership of g, and g has ownership of x. And intuitively, that allows me to regain a tree-shaped ownership structure. I own g, g owns all the nodes. The nodes do not own themselves, so there's no back pointers.
What's info and g?
That's a special directive that instructs the type checker to print out some information.
What
He wants to see it.
can you do info g?
Oh, sure.
Yeah.
It's not going to be very informative. Yeah, sure. It's going to tell you that G is a graph that has a root, which is a list of dynamic, and that it adopts nodes of integers.
So your cons is gone, but otherwise you have subtypes on the data type constructors. So
Yes, that is going to subtype to the nominal type, graph A, graph int, sorry. Yeah, I'm going to move on. So that's the DFS procedure. I'm not going to explain it into the detail. What happens here is the relevant bit. I need to visit node n. N is a node that is dynamic, so I'm taking ownership of n from the graph G. So I regain, at this program point, I'm regaining the x at node permission. I'm doing my stuff with n. I'm calling the higher order function f on it. I'm appending its neighbors into the work list so that they are scheduled for visiting later. And I'm also remembering that n has been seen by writing into its seen field. And then once I'm done doing stuff with n, I'm giving up ownership of n again by passing it to the graph G. And only after that am I visiting other nodes. So I'm making sure that I give up my ownership before actually visiting other nodes. And of course, for that to work, I need to have a runtime mechanism. How do I guarantee that these operations are legal? What happens when take is written is that there's a runtime test. It dynamically checks that n is owned by g. And if I try to write take twice, it's going to fail at runtime. Yes?
Consider doing this at compile time and attaching the permissions of n to the permissions of g.
So conceptually, you can think of it as this. You can conceptually think of G as possessing a list of all the elements that it owns. In the implementation, we have something smarter, using a hidden pointer from n to G. When n is owned by G, it has a hidden field that points to G. When it's not owned by anyone, the hidden field is cleared out. And we check the hidden field of n against g in every operation. That's why we're passing both n and g in the take and give operation.
Yes, though I was wondering if you considered doing this management instead of at runtime, instead of using a runtime mechanism, doing it at compile time by attaching it to the type of G. So when you say give n to G, it actually attaches your permissions on n to the permissions of G for the rest of the program.
That is not something that we have considered.
I guess it's your escape hatch, so you would probably not want to do that, I guess.
So, I mean, this is essentially a trade-off, right? I mean, this is where you go from the static world to the dynamic
Absolutely,
world
that's our layer.
to simplify the type check.
Yes.
Because, I mean, otherwise you would have to quantify over all the nodes and
Yes,
into like
precisely.
sums over sets into stars.
That's our design choice. We wanted to say we keep the base layer of the type system simple. We don't want to have complex predicates like there exists a G which conceptually owns a memory region in which the nodes live and the nodes are pointing to other nodes from the same memory region. We don't want to express that. So our story for the user is clear. Whenever you have complex aliasing patterns, just use that runtime test mechanism and the whole system remains manageable. I'm just going to skip the type checking because it's slow. I'm just going to interpret the program. So I fail. OK. I'm doing the DFS by passing it the print function, and it's printing 10 because that's the value that's stored in my node. So let's see what happens if I do a violation. Like, let's say, classic rookie mistake. I'm visiting other nodes before relinquishing my ownership of n. So I take ownership of n. I'm visiting its neighbor, which is n itself, so I'm doing a double take. There's going to be an error message at runtime that says that a take instruction failed. The error message could be better. I'm going to just skip on that briefly. That's about all for that extra layer. It is very important. Otherwise, there would be a whole class of programs that we can write, like any realistic program. So this is about delegating the ownership of the individual nodes to the graph. The whole point is that dynamic is a duplicable type that conveys no ownership information. There's a runtime test that guarantees that the whole thing works. It's already about an hour, so I may go a little bit faster.
Yes.
I'm going to talk about the implementation of Mezzo. So I designed the language with my advisor, and I was mostly responsible for the implementation. So what do we have now? We have a working type checker, a compiler that emits OCaml code with obj magic. There was a big implementation effort for the type checker. We have a cheap module system. Well, not cheap. We have a module system, as you saw, which has several modules from the standard library. We have the error messages. We have all the visualizations that you have seen with the graphs that appear, the web interface, one other that I'm going to show very soon. And we have several thousand lines of libraries for about everything: mutable data structures, mutable trees, iterators. We have modeled the protocol of iterators, laziness, etc. Why is type checking Mezzo difficult? There's some very complex algorithms in the type checker. Type checking is similar to proof search in separation logic. You have a function call. You basically have to solve the frame inference problem. Extract from the permissions that you own just a minimal set so that you can run the function and leave the rest untouched. As you saw, permissions that are represented internally using graphs. And we have another algorithm that is similar to what is called in the field of abstract interpretation to a join in a shape domain. So I'm going to run another command. OK. So this program, I think I may be able to zoom in. This program does something very silly. In the then branch, it allocates a reference and returns a tuple whose two components are pointing to the same reference. And in the else branch, it's returning a tuple whose fields are two physically distinct references. So the type checker knows that on the one hand, we have this aliasing pattern, where we have a tuple, which is defined here. So let me just zoom out a little bit. A tuple which is defined here, a reference which is defined here. It highlights in the source code the locations, and an integer that comes from here. And here we have that other tuples with these other references. So what does the type checker do? Well, it's complex. You cannot say that we have a tuple whose two fields point to the same reference, because that would be not true here. And conversely, you cannot say that you have two physically distinct references, because if the code takes the then branch, you're going to have something that's not true either. So what the type checker does is pick an arbitrary side and decides that, well, the right component is the tuple, is a reference, and the left component of the tuple is nothing. It could have picked the other side. So that's an algorithm that we have. This problem never happens in practice. That's completely wacky. Programmers don't do that. However, I wrote that visualization to somehow try to explain to the user what is happening in terms of aliasing and the decision that we've made. Back to the presentation. The type checker also performs type inference. When we have a polymorphic function, we don't specify the type application. It is inferred. So it's kind of hard to infer because there's a lot of backtracking involved. You can have multiple permissions for the same variable. You always have x at equals x. You also have x at dynamic. You also have x at ref something. So there's a lot of different solutions to explore.
You're sacrificing the notion of a best type then, because you make this arbitrary choice.
Yes, it is very difficult to have a best type. We have guidelines, like we know how to write the best type for a function. We can show the equivalence of several types together, but yes, the type checker makes arbitrary decisions. There's a lot of heuristics. Like there's been a lot of fine-tuning, and I would say in 98% of the cases, the type checker goes to the right solution immediately. And in some very complex examples, like iterators or something, there's a lot of backtracking involved, and the type checker is still able to do it. There are,
Do you have a characterization of the hardness of the type checking problem?
yes, it's very hard. I mean,
NP hard, NP complete, or?
I would say it's NP complete, just because we have quantification over permissions.
Yes.
So we can say for any permission P, and then if you want to infer that permission P, you have to try every possible subset of the universe to figure out what could be that permission P that you have to pass to the function. So in those cases, we have heuristics, like we may quantify over a certain P for map. The map function says that the small function that's being called repeatedly may have some internal state P, and then because our function types are annotated, the type checker is smart and knows that the function that is passed to map tells you which P you should seek to obtain. But in the general case, you have to annotate. Yeah. The type checker also produces a typing derivation if someone wants to check it later. We don't do it, but we may want to do it later. And there's also other extra modules that perform fixed point computations. We have that thing called facts. The type checker is aware that list of A is duplicable as long as A itself is duplicable. So that's something that is computed using a fixed point because of mutually recursive data types. Quick wrap up on Mezzo, language that blends many ideas. We are keeping everything presented as a type system, gives you strong guarantees, and there's that escape mechanism when the base layer is not enough. What do we want to do in the future? We want to extend the language. We may want to have some patterns where you own a piece of mutable data, but you may want to share it with someone just as read-only. There's another big question that has been somehow keeping us wondering is that if you're going great lengths to prove a program, how much does that help you prove it? You already have a very clear ownership structure. Is that something that helps you prove functional correctness? Can you leverage what the type checking of a Mezzo program gives you in terms of guarantees to help you prove the functional correctness of your programs? We may want to try to express proof obligations as type checking operations as proof obligations for an SMT solver, see if that works better or less than our custom algorithms. And we also want to explore visualizations. So you've seen quite a few visualizations that were mostly in the web browser. The reason is I've been contributing to Mozilla. I wrote some major add-ons for Thunderbird, and I also wrote a book about developing add-ons for Firefox. And my big add-on is called Thunderbird Conversation, gives you a conversation view in Thunderbird just like Gmail. So it's been interesting in the sense that add-ons are not written in standard JavaScript lingo because they're written using the internal version of JavaScript that lives in the Mozilla products. I get access to some nice features from the next versions of ActiveScript. That is destructuring assignment. That is a function expression. There's the let keyword, iterators for each, etc., etc. So that is that research. However, it's been nice for the error messages that I've shown you, the ones where you can see the graphs and click on the nodes to see where they're defined, and also for the, sorry about that, step-by-step examples. So, whoops. Yeah, I don't think I'm connected to the internet, so it's going to be kind of hard. Can I do that? Okay. MSFT open.
People are anxious to leave, I guess.
Okay. Okay, I'm going to do this real quick. Let's click on the tutorial, connect. Okay, let's click on the tutorial again. This not loading. Okay, I'm going to get back to it later when it's loaded. The web interface that you saw, it all runs in the browser. I've compiled the Mezzo type checker into JavaScript using a thing called JS-Avocamel, and it only required minor modifications. Our dream is to have an interactive top level when you can go back and forth and explore the permissions as they come and go in a visual manner. I think I'm reaching the end of my allotted time, so that thing does not seem to be intent on loading, so I'm just going to...
Are you able to connect to anything else?
Oh, yeah, it works. So that's the unfinished Mezzo tutorial, but what I wanted to show is that thing, which kind of helps me in the tutorial explain what happens to people. So you basically have two boxes with the duplicable and the non-duplicable permissions, and you can step through the program and see the permissions as they go back and forth, and explore things as they happen in real time. That is not auto-generated, that's handcrafted. I wish for it to be auto-generated, so that's one of our goals, because that's really a nice way to explain how programs are type-checked. And really, we wish to have everything blended together, where you edit the program, step through it, see the permissions. That's more involved. So really quickly, why am I here doing that presentation? I am interested, research-wise, in better verification tools. What I learned with Mezzo is that it really is hard to provide a better experience for users, especially as things get more complex. There's a lot of things to explain. I've been spending an hour explaining Mezzo to very competent researchers. I don't know how we can explain that properly to a user. We need to have better tools. We need to have visualizations, interactive stuff that really makes it easy to understand what's happening with your program. And I believe that these are research problems. The algorithms, for instance, to select the relevant bits of information that you want to show to the user, that's completely non-trivial. Showing aliasing, drawing the graphs, is that a good way to explain stuff to the user? That's not clear. And the tooling, I've been implementing that thing in the web browser, and it's great. I mean, people love it. They can go onto it. They don't have to install Mezzo. There really is something to explore. But how? How do we do it? That is also another question. User studies, user interface, user interaction, that's not something to be taken lightly. There's a lot of real work to be done. And I really do believe in the web-based tools. You reach more users. You have more impact. Deployment is made much easier. And I really believe that there's something to be done here. That is something that's been explored at MSR2. Can we have an ultimate web-based IDE? I think that's a valuable research question. So really, what I would be eager to do is leverage the experience that I've acquired with Mezzo to contribute to the projects that are being developed here. On two axes, there's the types axis. There's a lot of projects that rely on types. There's Coca, a type system with control of effects. That's something that talks to me, right? Speaks to me. FSTAR, iterations on design, type system. There's also Lean. Do we want to add separation logic theories into Lean? Can we somehow reuse the implementation techniques of Mezzo, all the heuristics, all the algorithms that pretty much do the same thing to teach that knowledge to the SMT solver? There are programs to be written in FSTAR. So really, that's a lot of experience that I would be eager to apply to existing projects. And also, I think all the visualizations that I've shown truly express the fact that I'm interested in what happens on the web. And I think that's something that is taking place here. Two things that I'm thinking of are Rise for Front and Touch Develop. And I believe that is something that I would be very eager to tackle and see what I can do about this. I've been trying to do it but I don't have, I'm just only one person, so there's only so much I can do on these web examples. They need to be integrated, and I think that there's a lot of potential here. I think I've overlapped a little bit, but that was good, so thanks for the questions and for your attention.
I have one question. So there have been previous attempts to create type systems that work for avoiding data races. Have you looked at any of the kind of programs that those efforts have looked at? Especially parallel algorithms, I guess, would be a good test for a type system.
One program that I wrote recently was like that very textbook example of a concurrent queue, where you have threads waiting on a condition variable, and you have to make sure that that is something that is very neatly typed in Mezzo, because we have a dependent type that says that the condition is that of the lock called L, and it like already rules out several errors where you broadcast a condition with the wrong lock or you mess up. So that would be pretty much the standard paradigm. One thing that we've wanted to explore is that here the graph G that I showed is uniquely owned. So you cannot have two concurrent threads trying to take from G at the same time. They need to have a lock on the graph G before they can take nodes out of G. That is due to the internal nature of the thing. Having G uniquely owned guarantees that our mechanism is sound in a concurrent setting. What we'd like to do is extend that give and take paradigm to objects that are immutable. So for that, you need a compare and swap operation, but that is still feasible. So that maybe would be a novel way where you have a built-in paradigm for expressing people that try to take maybe jobs out of a queue concurrently and possibly fail. So that would be a failable operation.
So how about something simple like parallel merge sort?
Parallel?
Parallel merge sort? Parallel sorting?
The one where you've, yeah. I guess that would, I didn't write it, but I don't see any difficulty as long as you do it with lists.
The difficulty usually in that case is that you're talking about indexes into an array, so you have to reason about which index.
That's why I said lists. With an array, it is very difficult.
Okay.
We've had an intern work on that, and if you have arrays, you have to start talking about arithmetic portions of the array, who owns the array from those indexes to those other indexes, and that is something that is still an open question in Mezzo. Merge sort works well as long as you use lists. So you do the partition, you get two different lists, spawn ownership, and then merge them.
Okay.
That works. With the array, I don't have any answer for the array.
I have another question.
Mm-hmm.
So, if your type system is in place,
Mm-hmm.
what are the kinds of programming errors that would be avoided?
So the first big guarantee is that programs written in Mezzo are data race free. So that rules out every access to mutable data that is not protected in some way or another. That really is our big motto. Another thing that we're trying to sell is that we have that mechanism for expressing intermediary states. So there's patterns where you progressively initialize objects. So that's something nice that we can type check as well. But really, we did it. We built everything from the ground up with the end goal being to have an answer for concurrent programs.
There's a piece of work that Matt Parkinson was doing with the Midori team on the M-sharp language. I think it was published in eCoop a few years ago. Many aspects of the system seemed a bit like that. Are you familiar with that work? And
does not seem to ring a bell.
So, why did you choose specifically, like, with the going with the functional languages? And how much of this could you transfer to other languages? And like, because people try to do similar stuff in imperative languages. I mean, OCaml, of course, is kind of on the both sides. But still, what was the main force you've went there, and how much of it applicable in other languages? And like type qualifiers is something that comes to mind, like when people try to model these similar things.
So I would say, so there's 2 points that I can bring here. The first one is that it's mostly a cultural thing, in the sense that in the team we're very familiar with OCaml, so initially went for like something that goes a little bit further than ML. Another thing that may be worthwhile is that I don't know if you heard of the Rust project at Mozilla. They're pretty much trying to do the same thing, a language with a control of ownership and effects. They're not using the same mechanisms, they're using lifetimes instead of permissions, but the goals are the same. But they're in a much lower level setting, in the sense that they're talking about what is allocated on the stack, what is allocated on the heap. And that makes their lives much more difficult, because they have to talk about the different varieties of objects depending on where they live. And that is something that we do not have. So I think we simplified our lives by going into the ML setting. Everything's heap allocated, everything's passed by reference. There's a garbage collector. And that allowed us maybe to focus more on the design ideas rather than the interaction with the low-level world. So I guess the ideas are applicable to a wide variety of languages, but they would probably run into some concrete issues if you try to apply them, say, to a language that has stack versus heap allocation. Yes?
So I'm interested a little bit more about the object layout. Now I noticed when you were writing the types, like the intermediary types that were, I believe you said, not derived from a nominal type?
Yes.
So you had them written out as you would have the tag, and then you have an open curly, and then you have named position labels set to be types.
Yes.
So you can only change the tag to other nominal types that have the exact same position labels and the exact number of fields?
No. The name of the fields do not matter.
Okay.
Only the size of the block matters. If you change from tag A to tag B, your thing gets renamed with the fields that belong to tag B. Okay. So we're structural for the field names in the sense that they're updated as you mutate the tags.
Right. And then the second thing is, so because you can exchange the types, you can exchange the tags between pretty much anything, that I assume that means that all of your tags then have to be assigned unique ordinals across the entire program space then?
I don't think so.
How do you distinguish between the tags, I suppose?
Well, type checking gives you runtime safety. So we know that the compilation is going to be fine.
So you don't actually so those are not actually tracked at runtime then?
Well, it's just the tags exist at runtime. The compilation model is that when you have a data type with several tags, they're allocated in sequence, right? 0, 1, 2, 3, and then that's used for compiling pattern matching to discriminate on the tag. That's all we need. So we just need tag numbers to be distinct across branches of the same type.
Right.
That you just need that to compile a pattern matching properly.
Right, and you can't pattern match between different nominal types.
No,
even, right?
you can only pattern match on things from the same nominal type.
So when you passed ownership with the give, that also gave the type to the n, right? I mean, when you took ownership from the graph and put it like, I guess, to a procedure or whatever, that also gave type to the variable. Because before it was list dynamic, and then after that.
Yeah. So we look up the definition of G. We see that G adopts node A. I don't know if you remember.
So it can then only adopt one type.
Yes, it would be unsound otherwise.
Okay.
And that is something that we have exported as well, and you can only have one object adopt one type.
Okay.
Or you just do a variant type if you want to have an object adopt multiple things. Like you define a new type, thing A of thing A, else thing 2 of thing 2.
Let's thank Jonathan.
Thanks.